My name is Devendra. I'm very excited to be here. I'm a researcher at Mistral AI. A little bit about myself. Before joining Mistral, I was a research scientist in Facebook AI Research Lab. And before that, I did my PhD at Carnegie Mellon. And before that, I was in India for my bachelor's. So today, I'm going to talk about Mistral AI's LLMs. And specifically, I'm going to try to dive in behind the training strategies that we use to actually build these LLMs and try to describe the overall process and the building blocks needed to build these really large models. So a little bit about Mistral. We started last year in June with a seed money of around $113 million. We released our first model in September last year, the Mistral 7B model. It is still one of the most popular 7B model out there. It's one of the first model of the 7B size that was small enough to be used on laptops and phones, but at the same time useful enough that people could use it for multiple tasks like summarization, rewriting, and things like this. In December, we released the Mistral 8x7B model. This is one of the first sparse mixture of experts large language model. And it was, I believe, the first open source model that was able to reach the ChatGPT 3.5 performance. And at the same time, we also released Mistral Medium and Mistral Embed, two of our commercial models. Medium is a larger model with even more reasoning capabilities, and Mistral Embed is our embedding model. And all these models were available on our platform as API endpoints that we started again in December. And then in February, we released an even larger model, Mistral Large, which is our flagship model with the highest in capabilities in terms of reasoning, coding, math, knowledge. And we also released our chat interface, Le Chat. It's available free to use even now at chat.mistral.ai. And then in April this year, we released the 8x22B model, which is a larger sparse mixture of experts model. This is also an open source model at the time of the release, it had the best performance among all open models. And very recently, a couple of weeks ago, we released Mistral 22B. This is a model optimized for code. So it's very good for coding assistance. It can be used as a co-pilot in your coding platforms, and you can also ask it coding-related queries. And it's a very small model, a 22B, so it's really fast. Because it's optimized for code, it gives really good performance. Some people have given us the feedback that it's comparable to GPT-4 on coding tasks. And also, this model is freely available on our chat interface. So you can go to chat.mistral.ai and just select Mistral and use the model. And then yesterday, we announced our new funding round, the Series B funding round of around $640 million at a $6 billion valuation. So in the last 1 year, our company has grown around 25x in terms of valuation. And this will allow us to scale even more, like build even better models and more tools for the developers to use these models. So our mission is to build the cutting edge AI that can be used by everyone. Specifically, we have developers in our mind, and there are some principles we use to build these models and our platform. So the first one is openness. So I believe we have pioneered the open source models. Many of our models have been released with Apache 2 license, which means they are free to use even for commercial purposes. And we want to continue doing that. We want to continue releasing the best-in-class open source models. And the second is portability. We remain an independent model provider. Our models are available on all hyperscalers, Azure, AWS, GCP, even Databricks, Snowflake. You can also deploy our models on virtual private cloud or on-prem on your own servers. So this allows any enterprise to use our models because we are practically available in any form the enterprise may want. And we are particularly optimizing for value and speed, or in other terms, we want to provide the best performance to speed ratio. And this is something that our models have been really good at. So we want to train smaller models with better performance. And this turns out to be really useful for real-world applications because this reduces the latency and reduces the cost of running these models, but at the same time, you get the performance you want. And the last one is customization. We have our platform and we have a bunch of developer tools that we are building and that we are open sourcing for the developers to easily use our LLMs and build the applications on top of it. So, for example, we released our fine-tuning library, Mistral Fine-Tune, and before that, we released our inference library, Mistral Inference. These are again open source libraries, free to use, and they are optimized to easily use LLMs for any application that you may want to build. So among our open weights models, we have, in the general purpose category, we have these 3 models, 7B, 8x7B, 8x22B. And they are in increasing order of size. They perform, the performance increases as we go from 7 to 8x7 to 8x22. And they are multilingual. They are specifically natively trained in English, French, Italian, German, Spanish. And they also work pretty well for many other languages. And the best part is that all these 3 models are Apache 2.0 licensed, so it means that they're free to use for any purposes, including commercial. So I'll go a little bit deeper into these models later on. But before I do that, I wanted to talk about how these models are actually trained. It helps in understanding how these models are trained, even if you don't want to train them yourselves, but want to use them to their fullest potential. So I'm going to give like a general overview of the LLM training process, and this is like widely followed in the industry across all top AI research labs. And typically we have like 3 stages of LLM training. The first one is pre-training, and then instruction tuning or fine-tuning, and then the last one is learning from human feedback. So let's talk about pre-training first. So the pre-training process is very simple to define. You can just take some piece of text. Typically, like we use the open web to find like the text. And then the task is very simple. You feed these tokens or words from your text source into the large language model, and you ask it to produce the next word or next token. And you just repeat that. So it's very simple to define. All the model is learning is to predict the next word. But in practice, it is actually very hard. So first of all, we don't use words exactly. We use something called tokens, which are roughly like 0.75 word. This allows us to trim down the vocabulary size because the number of words across all different languages is a lot. So if we tokenize them, we typically get vocab size of like tens of thousands of tokens. In our open source models, we use 32,000 tokens as the vocabulary size. And then each token is basically represented as an integer. And so what the model is doing is like taking in an integer and predicting the integer for the next token. So it's just integer to integer mapping in a sequence. But in practice, it's really hard. Why is it hard? because it takes a lot of time to process these data sets. The data sets are huge. They're typically, trillions of tokens, can be 10 trillion, 20 trillion tokens. It requires a lot of steps, pre-processing, cleaning, deduplication. There's a lot of noise on the open web data. And this is, I believe, a very common misunderstanding. People think that you just get more data and that will lead to a better model. That's not necessarily true. Your data needs to be clean. If you get more data but it's noisy, it might not lead to better performance. So it's very hard to get this right. Internally, we just say that the data can never be perfect. You can keep cleaning and it will keep becoming better and better. So the question is, how far can you go or when do you stop? And then the next part is it costs a lot of compute. It's extremely expensive. So these models are huge. They can be like hundreds of billions of parameters, and they require tens of thousands, now even hundreds of thousands of GPUs to train this over many months. And so each model can cost 10 to 100 million or probably even more these days. And this is extremely expensive for any academic lab to run or even small companies. And then the hardest part is actually that you get only one chance. Each model training run costs tens or hundreds of millions of dollars, so you cannot try multiple times. If you try to train something and the model training fails, you usually don't have the budget to do another one. So you need to get a lot of things right. So you need to decide the model architecture, you need to decide the hyperparameters, the data mixture for what we call the big run, because it's going to run for multiple months. And you might think that best hyperparameters for a smaller model might be the same one for the large model, but it's not true. So it's really hard to get all these things right. So on the right, I'm showing the data mixture for Llama pre-training, Llama 1 pre-training. And then you might think, how did they decide that GitHub should be 4.5% and not 5% or not 10%? And the answer is that we don't know. This is just based on intuition of people who have done this before, and they decide on something, and even they don't know that is the optimal decision. There is no way to know, because we can't be training hundreds of these models to figure out, okay, what is the best data mixture. And the same thing with model architecture. Why are there 32 layers in 6.7b? Why are not there 34 layers? Again, we don't know this. Something that people decide based on intuition, and then there's not a lot of experimentation or science behind it. Okay, so once we train the pre-trained model, can we use the model directly? So let's say you wanted to write a Python function to find whether the input number is prime or not. And so if you give this prompt to a pre-trained model, what happens is, because the model is just trained to predict the next token, it tries to continue the text. So you have the model completing, it's giving example of input-output pairs for this question, as you might see on some coding blog on the open web or something, right? But there is a trick. What you can do is trick the model by giving it a function definition. You just provide the function definition in Python and provide a docstring that this function takes an input integer x and returns true if x is prime and false otherwise. And now the model gives you the right answer because it's trying to complete the text, and this is the most probable text for that prompt. So this shows us that the model actually knows the answer, but it's not aligned with how humans want to use it. So this is really cumbersome for every human to write a function definition like this, or figure out some way to prompt the model so that it gives the right response. So this is why we need stages 2 and 3 of model training. to align the model to interact with humans in the way they prefer. So the next step is instruction tuning. Again, the concept is very simple. Now, instead of just text data, you have prompt response pairs. So you have a prompt, like write a Python function to find whether the input number is prime. And then you have a response, which is the Python function. And the only difference from pre-training is now you start predicting the next token only for the response. And you're not asking the model to predict the next token for the prompt, because that's given as, the whole prompt is given as input to the model. And then we have this special tokens for the beginning and end of instruction, so that the model knows that this is part of the prompt. And then after the end of instruction is what the model needs to produce. So in terms of data set, we have a paired data set of prompt response pairs. Typically, we use 10 to 100,000 instructions. And then the task is, again, next word prediction, but it's masked to not include the prompt in the prediction. And this requires way less compute. You can typically do this in tens or hundreds of GPUs in few hours or a couple of days at max. And then the last step is learning from human feedback. And the idea here is, like, it's much easier for humans to rank two responses rather than to, write the whole response from scratch. So if I show you, like, again, the same prompt, now you have two responses with two different functions of how to find whether the input number is prime. And I can, a programmer can easily say that, response 1 is better than response 2 because it's, looping over only till square root of x and not till x. But it is much harder to, like, write the whole function from scratch. So it's much more cost effective to do human preference ranking of responses. So if you can get, like, pairs of responses for the same prompt and you just ask human which one is better, that is way faster than just asking the human to write the whole response from scratch, right? And so that's why we do this step 3 to make the model even better with human preferences. And sometimes it's really hard for humans to come up with a response. Like, if you ask a human to write a poem about San Francisco, it's really hard for most people to do it. But if you are given two different poems, humans can easily judge that, okay, which poem they like better than the other one. So there are a lot of prompts for which, like, this kind of human preference data is much easily gathered than prompt response pairs. And so there are a couple of techniques you can use this kind of human preference data. So one is reinforcement learning from human feedback, which is fairly popular. So the idea here is, like, you have this kind of preference data that this response is better than this other response. So you train a reward model given the prompt and some response. It assigns a reward for that response. So lower reward for unfavorable responses, higher reward for favorable ones. And then you use this reward model to train your LLM using reinforcement learning. And the other popular technique is direct preference optimization, where you skip the step of training a reward model, which is fairly difficult to do to make it stable. So here you directly use the preference data and optimize the likelihood of these human responses. So you increase the likelihood of favorable responses and decrease the likelihood of unfavorable one directly without having to have a reward model. So to summarize these 3 stages of LLM training, pre-training requires the most amount of compute, most amount of data. It takes weeks or months of training. And then instruction tuning and learning from human feedback typically require 10 to 100,000 instructions, a few hours or a couple of days to do instruction tuning. The hard part of stages 2 and 3 is that you need to try multiple things to get this right, especially like if you have multiple data sources or you have humans annotating, but some of them have like noisy annotations. So you need to like filter those out. So it requires multiple iterations, but it's still much faster than the pre-training itself. So these are the 3 open weights models that I talked about earlier. So I can describe a little bit more in detail. So the first one, Mistral 7B, is a dense transformer architecture. The hyperparameters on the right, they are basically number of layers in the transformer, the dimension of the head, dimension of the hidden layer, the number of heads, number of KV heads, and so on. So this model we released in September last year, and although it's a 7 billion parameter model, it outperformed Llama 2 13 billion on all benchmarks, and then Llama 1 34 billion on most benchmarks. It performed really good on code. It was comparable to code Llama 7B when we released this. And this is the performance across different types of benchmarks. So MMLU is one of the most commonly known benchmarks for knowledge and a bit of reasoning. Then we have other sets of benchmarks for knowledge, reasoning, comprehension, math, code. So it does well across all the different benchmarks as compared to Llama 2, even 13B and Llama 1 34B models, while being just a 7B model. So that means that you pay a much lower cost to run this model at inference time because it's much smaller and also much faster to run. And then the next model we release is a sparse mixture of experts model called Mistral. It outperforms Llama 2 70B while being approximately 6 times faster at inference, 6 times lower latency as well. It was the first open source model to match or outperform GPT 3.5. It's multilingual by design. It's trained on English, French, Italian, German, Spanish. And it is handles a context window of 32K tokens, which was at the time more than GPT 3.5. And so the idea here is very interesting. For each layer, we have 8 different experts, and the model chooses 2 experts for each input token. So what this allows us to do is that we can increase the total parameter count. So the total parameter count of this model is roughly 46 billion. But at the same time, for each token, only 13 billion parameters are used. That means the number of active parameters are only 13 billion, but at the same time, you have 46 billion parameters to choose from. And so what this does is that the model has more capacity to store more knowledge. So it performs really well on knowledge tasks because it can store more knowledge, but at the same time, it is really fast at inference time because it's only using 13 out of the 46 billion parameters. And the way it works is like for every layer, we have a router. So router is a trainable neural network layer, which basically assigns weights to each of the 8 experts. And we pick the top 2 out of the 8 experts. So each token is routed to 2 out of the 8 experts for each layer. Many people think that, the experts are like, roughly semantic experts, like, okay, 1 expert for coding, 1 expert for math, or 1 expert for English. And that's not the case. That's a common misconception. So we have, it's not like there are only 8 experts. There are 8 experts per layer. And in this model, we have 32 layers. So that means that for each layer, the model can choose 2 experts. So you have option of 8 choose 2 at every layer, and you can multiply this. So the number of paths each token can take is actually a huge number. So we try to find some pattern in how the experts are selected, and the model learns that the experts are typically more syntactic in nature than semantic in nature. So syntactic meaning that one expert usually handles like prepositions, or one expert usually handles nouns, or that kind of stuff. But again, because their combinations are a lot, it's very difficult to even analyze all possible combination. So this is something like which is very like it's an emergent behavior. Like we don't select like what expert should be trained for what. We just let the model choose it, and it figures out what is the optimal way to use the experts. Across all the benchmarks, we have very good performance as compared to the Llama 2 family. So we are outperforming Llama 2 70B while having only 13 billion active parameters, right? Across, again, MMLU, knowledge, reasoning, math, code, and so on. And this is very interesting that here what we are trying to do is compare the performance of the model with based on their inference cost. So on the y-axis is like performance across different benchmarks, and on the x-axis we have the active parameter count, which is proportional to the inference cost of the model. So you can see basically our family of models, like 7B, 8X, 7B, they're way better than the Llama 2 family in terms of performance to cost ratio. Because the higher you go towards the top left, the higher performance you have at a much lower cost. So for just 13 billion, active parameter count, we can basically match the performance of Llama 2 70B or even outperform it in like by a large margin on math and code. And then after that, the 8x22B is basically a larger version of 8x7B. Instead of the 22B base model, now we have, instead of the 7B base model, we have the 22B base model. So we have more layers, like 56 instead of 32, more bigger hidden dimensions and so on. So this is just a larger version of the earlier Mistral model, and it performs even better as expected. And so here we are comparing with other open source models, the Llama 2 family and the Command-R family from Cohere. And again, like the top left corner is the best performance to cost ratio. So you're pushing the performance out of smaller models. And again, this is really helpful for application developers because you pay a much lower cost to run these models at deployment time. So if you're using the models, like let's say for millions of queries, this translates to much lower cost for the application you're building. So some practical tips. You might ask, when do we use commercial models? When do we use open models? Because there's a lot of models out there. Even we have our own open models offering and then the commercial ones. So for commercial models, the first thing you can try is prompt engineering, few short prompting, one chain of thought prompting, or something called retrieval augmented generation, where basically you ask the model to use an external knowledge resource to solve your task. For open models, you can do all of those things, prompt engineering, RAG, everything. But you can also do task-specific fine-tuning, which means that you take the open model and you fine-tune it for the task you care about, the application you are building. For example, let's say if you want to do a customer service chatbot on your specific database of frequently asked questions, right? So you can fine-tune the model on this database, and then it will, for a really small model, you can get a really good performance for that particular task. So this is what we call task-specific fine-tuning. You need a little bit of data and a compute to do this. So if you have those resources available, it's way more efficient to do fine-tuning and then deploy the models. And then the choice basically becomes a balance between performance and cost. So commercial models have typically higher general purpose performance, but open models can beat commercial models on specific tasks if you do fine tuning. And at the same time, because commercial models are larger, they have a higher inference cost. They're more expensive to run. Typically, like what I have seen from a lot of enterprises is they prototype with a really large model with the best capabilities, like GPT-4 or Mistral Large. And then once they figure out the application, they go to a smaller open source model and fine tune it for that particular task. And then the last thing I'll talk about is CodeStral, which is our code model that we released a couple of weeks ago. So it's a 22B dense transformer model trained specifically for code. And again, we are trying to optimize performance and speed. So we try to get the best performance out of a small model to make it really fast, at the same time really good. It's trained with more than 80 programming languages. And it has like both instruct and fill in the middle mode. So what I mean by this is instruct is what you use in a chat interface. You ask a model, write a Python function to do this. Fill in the middle is what you use in something called GitHub Copilot. So where you're typing some code and the model suggests edits in that code or additions. So it completes the code. So you can call it code completion or filling in the middle of the code that you are already have in your coding platform. So in terms of results, it outperforms Code Llama 70B, DeepSeek Coder 33B, Llama 370B, all like much larger models, while being significantly smaller at 22B parameters. And at the same time, we trained it with a longer context window of 32,000 tokens. So that means that you can do very long context or long range coding tasks. You can feed very large code bases into the model and ask it to complete new functions or new capabilities based on that code base. And it's good on both instruct. So instruct is the left side, the Python and SQL are instruct tasks. And on the right is fill in the middle task, FIM. So it's good on both types of tasks. And it's multilingual. It has more than 80 programming languages, including some really unpopular languages like COBOL, CUDA, which people are not super familiar with these days. But if you are working with, on editing some code, a really old language, the model performs really good at it. It outperforms all open code models on all these languages. So we have like benchmarks across Python, C, Bash, Java, PHP, and so on. And on average, it's way better than, again, models of more than 3x its size. So it's free to use on our chat interface, chat.mistral.ai. So you can select like which model you want to use. We have like large, small, CodeStral, and so on. It's also available on our API on Lab platform, which is our API access endpoint. And it's free to use for, I believe, the next 6 weeks. And it's also integrated with popular coding editors like VS Code and JetBrains. So here's an example in VS Code with this plugin called continue.dev. So you can ask it to complete code, ask it questions. Let's say, write the code in a different language. You can also, ask it to edit the document, like write doc strings for all the functions in this document. So it will just complete the doc strings. And we have been working with a lot of other startups in the open source community specifically. A lot of people really like CodeStral, and they've integrated it with their plugins and their products. So we have, here are just some examples. There are many more on our website. So from continue.dev, which is the VS Code plugin, we have JetBrains AI, Llama Index, and so on. We have offices in Paris, London, and here in Bay Area. We are actively hiring. We just closed our Series B round yesterday. So if you are interested in building the next generation of AI models, please do apply. And I'm happy to take any questions. Thank you for your attention.